Hello, everyone. It's a pleasure to be here virtually with you. So I'm Max Decoto. I'm a professor at the University of Sherbrooke. I had the privilege of having Helef Terios as a postdoc way back in 2012, 13, and 14, and lots of the DIPY tools and DIPY mentality I've been adopting and promoting for years now. So I'm very happy to be here. Today, the plan is to separate my talk in several parts. And so you'll see that in the first part, we'll talk about spherical function. What does it mean for a signal to live on the sphere? How do we represent it? What's the diffusion signal? What is the apparent diffusion coefficient on this sphere? I will introduce also spherical harmonics. And in other parts, we'll get into cue ball imaging, diffusion ODFs, constrained spherical deconvolution, and eventually into multi-shell kind of data with the diffusion propagator and multi-compartment, multi-shell spherical deconvolution. So let's start. Just to give you a brief introduction, the holy grail of diffusion-weighted MRI is to reconstruct at every voxel this object that I call the diffusion propagator, this P of R, the diffusion propagator. So keep that word in mind because this will come in the last parts of the demonstration with all the diffusion propagator techniques. And visually, this means that at every voxel of the brain, right? So this is on the order of millimeters, let's say 2 by 2 by 2, we have this object P of R in every voxel. So this is very complex object. It's a 3D function within each voxel, right? Because this R here is a vector, and this is a radial component R, an angle theta phi. Okay, so it's doable today, but way back when diffusion started, it was impossible to reconstruct such a large 3D function at every voxel. So as you will see, we will need to make some simplifications to summarize this maybe just on a sphere, right? If we just keep here theta phi, then we're left with just a spherical function instead of a whole 3D function. And so this is the only equation, critical equation linking the signal S of Q and S0, this is the B equals 0 image, with our object P of R. So I'll change color here, but P of R here, which is our diffusion propagator. And so for the physicists out there or engineers, you see it's related via a Fourier transform. So we measure in Q space. Here Q space is actually in millimeters inverse, right? So we're measuring in frequency space, and the object that we're interested in, the P of R, is in millimeter. It's in real space. So P of R is really in the space of axons and at the scale at which we want to reconstruct features of the white matter neuroanatomy. All right, so with this equation, we see some basic math. So this S of Q, right, which is the Q space signal, and Q here is a vector in 3D. R is also it's a real space, and it's also a vector in 3D. And what you see here appearing for the first time is the ODF, which only depends on theta and phi. So this is a spherical function, where here we've integrated, sorry, so I'll remove we've integrated the radial part to have a sphere. Okay, and this will come back in some code later. So this is a 3D object, this is a 3D object, this is a 2D object. And this will have an impact on how we deal with it in DIPY. So a spherical function, SF. In a lot of the DIPY code, you'll see SF, sometimes the acronym. This is spherical function. What does it mean? Well, it simply means we have a sphere. So here illustrated by this grid, this spherical mesh, and you have a number at every point on this sphere. And you will see in my demo, we can have several points, like hundreds and thousands of points on the sphere, or just a few points. Like if you're doing DTI acquisition with 32 directions, well, you have 32 such theta phi, 32 direction. So you have a number for each of these points. So either you assign a color, or something we always do is we actually scale the radius of the sphere according to the value, right? So the value here is 0.9 and here is 0.6. And so the radial amplitude of the sphere is actually the value. So this gives us a good visual representation of the spherical function. But in a sense, it's just like a 2D image, but we don't have a pixel grid. Here we have a mesh, a spherical grid. So we're in a manifold, a 2D manifold parameterized by theta and phi. So this is a spherical function. So keep that in mind. As soon as you see SF in DIPY code, it's a spherical function. Right. So I just want to come back to this overview of the talk. So we have this link between the diffusion propagator, P of R, our signal S of Q in the 3D world. And today, you have other demonstration this week by other talks. We're taking this route here of not tissue model, so not biophysical modeling of the tissue like the NADI model or their multi-tensor model. Here we're taking the route of model-free techniques. So we're just going to play around with mathematical tools that allow us to capture the diffusion signal, the diffusion ODF, the ODF, or the diffusion propagator. And so lots of options to measure the signal Q, and we'll see a few of those options today. So either you can measure Q on a grid, this is often called DSI, or Q space imaging, depending on this grid. There are radial sampling schemes that are less popular, but otherwise, when we talk about single shell, this is single shell versus multi-shell, which in a sense means single B value versus multi-B value. And so anything within this sampling scheme will have an impact on the spherical function, on the propagator, on the ODF you can extract. This is just another representation where this is DSI, this is single shell, and this is different multi-shell versions. As opposed to the first row, which is more the classical DWI for one direction, for XYZ direction, 1D Q space imaging, or the basic 6-directional DTI. Right? So today we'll mostly be focusing on single shell and a bit of multi-shell data. Right. So spherical harmonics. Why do we need spherical harmonics? Spherical harmonics are a basis function for any spherical function on the sphere. Just like sines and cosines for Fourier transforms in imaging, spherical harmonics is basically a Fourier transform on the sphere. So just a reminder for everybody, what is a basis? For instance, here you have a basis example of the canonical X, Y, Z directions in 3D, right? This is X, Y, and Z, and you can basically reconstruct any 3D point by a linear combination of red, green, blue, or X, Y, Z, right? So if you take any X, Y, Z, you can compute it by X times red plus Y times green plus z times the blue vector. Well, spherical harmonics is the same idea. You can actually reconstruct any spherical function on the sphere just with a series of spherical harmonics coefficients. It's just a bit more complicated than the x, y, z vectors, because in principle, or in theory, you have an infinite number of spherical harmonics, a bit like the Fourier transform. So we're going to have to truncate our basis for a specific order. So it has a mathematical formulation. You see a complex number here. It looks like a sine and cosine on the sphere with a normalization factor. Let's not focus on the math. You guys can read that on your own. But essentially, the picture here is the most powerful one. That is, given any spherical function, you can actually express it as a linear combination of a bit of a sphere, a bit of this guy, a bit of this guy, and a bit of this guy, to reconstruct my crossing fiber here, for example, which would be the spherical function that I'm trying to express. So it's a way, a model-free way to reconstruct the signal, but also in a way to compress it, right? Because if you have thousands of points on the sphere, or even just 32 diffusion-weighted images, you can actually just project that on a few, in this case, 15 coefficients of the spherical harmonic spaces. And so given a certain grid and a certain sphere for a certain B value, this is single shell acquisition. So you have, you know, a diffusion weighted image for each of these points. So this would be diffusion weighted image 1 for direction 1, diffusion weighted image 2 for direction 2, diffusion image 3 for direction 3, and on like that. This would be a spherical function, right? dWi for each direction. And we could project that on a spherical harmonics basis. And the way to do that is basically to implement a Fourier transform on the sphere. So given a signal on the sphere and your basis elements, you're just trying to find the coefficients. How much of this element you need for this representation. And there's really nothing else to that. So finding the spherical harmonics coefficient of a diffusion signal, whether it's a spherical function, the diffusion data itself, an ADC or an ODF, it's always the same process. So DIPY will allow you to build this matrix. This, we often call it the SH matrix. And given any signal, will return to you these coefficients C. So, and this is actually the algorithm that's going on. There's a small regularization going on, but DIPY will build these different matrices and implement this least squared or pseudo-inverse spherical harmonics transform to provide the coefficients. And so this is a great way to go from any sphere to the basis, and then to also go to another sphere, let's say for visualization. So this will, you'll see that in my demo, but with this tool, it's easy to start from, let's say, DTI data from 32 directions, go on the spherical harmonics basis of 15 coefficients, and then project back to, let's say, 5,000 points on the sphere to have a sexy visualization. Because only this B matrix will do the trick of extrapolating data to a bigger sphere, if you wish. There's also in practice, a small regularization parameter coded in DIPY. So this is why it's called the inverse, pseudo-inverse smooth. So this comes from several papers and years of research. You shouldn't really have to play with that, but it's good to know that we do actually have a small regularization just to stabilize the spherical harmonics transform. So I'm going to take a break here and cut the video. and then switch to my demo to just show you what that looks like in practice. So I'm going to take over here. So I've given you 2 Jupyter notebooks. One is part 1 and part 2 with a requirements file. So you can just on your Linux or Mac pip install the requirements, which will go fetch the right DIPY, Jupyter notebook, and all that. You can then just call Jupyter notebook. This will launch in your browser, and you will find these 2 tutorials. So let's start with the first tutorial, which is DIPY tutorial on reconstruction of the diffusion signal. So you can just run the first few things. I'm going to get the DIPY modules that we need for this. So a little bit of Fury for visualization and some of the basic imports to simulate voxels, to extract spheres and play with spheres and different signals, just to illustrate what I mean by a spherical function and a spherical harmonic. So these are just visualization tools. You can read the code or get inspired by this, but I'll just run them. So first, the apparent diffusion coefficient versus spherical harmonics. So let's just start by this little block of code here. So you'll see I'm generating 64 directions on the sphere. So this looks like a single shell at b value 1000 data with 64 directions. And I could change that to 32 or 100. You can play with this code. I'm going to generate the 64 randomly generated directions on the sphere for that, on the hemisphere, and then I'm going to spread them out over the sphere using the dispersed charge algorithm. So this is the static repulsion force algorithm from Derek Jones to more or less distribute 64 directions uniformly on the sphere. And then I'm going to create my classic gradient table for diffusion. And you see I'm printing in it here. I'm adding a B0 image. So a B0 image is with a B value of 0 and a vector of 0, 0, 0. And then you see my 64 directions, which are just X, Y, Z, X, Y, Z, X, Y, Z. And I'm also adding a last B0 image. And these are my B values. So if I run this, and I show you what it looks like, this is a 64 directional scheme uniformly distributed on the sphere. Something I could export in a text file and then bring to my MRI scanner to actually run a diffusion weighted imaging protocol with these 64 directions. Right? If I had 12 directions or 32 directions, this would be a DTI-like protocol. Now here with 64 directions, this is more like a hardy single shell B1000 protocol. So now I have my grid, right? I have my sphere. Now I can assign values to these green points. So here's a small example to generate signal in DIPY, either with 1 fiber, 2 crossings, 3 crossings, you guys decide. Right now in my example or my demo, this is fixed to 2. And I'm generating a simulated multi-tensor signal. So this is the most traditional and simple way to generate fake signal. So let's run this. And as you can see here, this looks like a signal now on the sphere, right? I just have a ball with numbers on it, just like in my slides. It has a bit of a weird shape, so let me just change this to a 1 and run this. And run this little code here. So a single shell, a single fiber signal looks more like a disk or a sphere with a big ring. Now, so this is more familiar if I run this code. Right? The only difference here between these 2 calls is that I said, please normalize the sphere. This is true now. So on this top example, the sphere is not normalized, false. And here on this bottom example, this is a normalized signal. So it looks like the famous single fiber donut. Right, so the fiber here is aligned with the blue area. So I'll put this back to 2, just so you have an idea of what it looks like with a 2-fiber signal, which complicates things and looks a bit weirder. It looks like doesn't look like much though. So that's the first thing to note, is you would never want to start doing fiber tracking on this object. You can see that actually the signal is blue, is the weakest where you have well, or some directions. All right, so this is a spherical function. So values on 64 points of the sphere. Now, if I take the log of this signal, I actually get the ADC. So we'll go back to my slides and see that. But the apparent diffusion coefficient is related by an exponential, a negative exponential. So you just taking the log of the diffusion signal, you get the ADC. And so suddenly the ADC now looks more, like a crossing fiber object. Turns out to not be properly parameterized to do fiber tracking, but you at least see that this object is a 2-fiber compartment object. So again, the non-normalized version versus the normalized version. Okay. And finally, in this little demo, that what I want to show you is the spherical harmonics. So now if I get the spherical harmonics model from the reconstruction module of DIPY, I can really do a lot of things. I can declare a matrix of order 2. This will be just a 6x6 matrix that looks like DTI. Order 4 will be 15 by 15. 15 by the number of directions, sorry. And order 8 will be 45 coefficients. So if I play this, you can see that at order 2, I have 6 spherical harmonics, order 4, 15, order 8, I have 45. And now I did, the last thing I did is I got a sphere from DIPY that's a lot more tessellated. So it's not these 64 directions that I had originally, but now I'm loading 724 directions on the sphere, and I'm subdividing it by a factor of 4 or 2, which gives me a sphere with 11,000 points. So this is a crazy, very highly tessellated sphere. And you'll see why I do this. This is just to have good visualization. And so suddenly, you see suddenly my sphere is originally not super tessellated, but if I use my super sphere, you can see the difference here. So here I have 11,000 points on this sphere versus this one that has 64 points. And if you missed the math, so I'm going a bit quickly, but you guys can dissect this and digest this later while you go through my code. Well, to get the spherical harmonics signal, as we saw in my slides earlier, I'm taking the pseudo-inverse, so the dot product between the inverse of the B matrix and the original signal on the sphere. So this is a spherical function. This is the B matrix, so the SH matrix, and what I get as a return is the spherical harmonics coefficient. You see the math here in comments. And so I have a way to go from the sphere to the coefficients and back to the sphere with any spherical harmonics matrix, right? Because then I can apply the highest resolution B matrix to go back to the sphere. So it's a very nice way, a linear transform way to go from signal to spherical harmonics back to the sphere for any resolution we want. So the 0th order spherical harmonic is the sphere. The second order spherical harmonics looks like a diffusion tensor, and the high order spherical harmonics allows us to get crossing factors.